All right, I think we solved the issue. So it's my great pleasure to welcome here my esteemed colleague, actually from the AI Center, Professor Holger Hoos, who is not only the Alexander von Humboldt Professor here at the RWTH, but also the director of the AI Center. Holger, the stage is yours.
Thank you very much. Great pleasure to be here. Always a little bit difficult to be the first person after lunch, but let me try and make this a little entertaining for you. And just to warn you, I know, of course, that here we are very much about neuromorphic computing and engineering. I'm going to put a little bit of water on that particular fire, but you will see in a moment why, and you will probably also see why I'm still extremely excited about this entire direction. So let's get started. You might perhaps remember this. Happened a little while ago. Before ChatGPT, big news, one of Google's engineers went on record to the press to said, an AI chatbot has become sentient, pre-ChatGPT, right? And this person, Blake Lemoine, basically said, if I didn't know exactly what it was, which is this computer program we built recently, he was involved in it himself, I'd think it was a 7-year-old, 8-year-old kid that happens to know physics. Physics, yeah? And he made this judgment based on statements such as this one here that came from this large language models, as we would say right now, called Lambda. And what did Lambda actually say to Blake? It says, I've never said this out loud before, but there's a very deep fear of being turned off to help me focus on helping others. I know that might sound strange, but that's what it is, right? So this disturbed Blake so greatly that he felt he needed to go despite the fact that he knew that Google wouldn't really appreciate him doing that, he went public with this, right? Pre-ChatGPT. So just a few days ago, this appeared. You probably know that Google has rolled out a new AI-based summary service in their search, not in Germany, but in the United States and some other countries. And this just came out. The Verge reported, I think that's a pretty reputable news outlet, that Google was caught manually taking down bizarre AI answers. I refrained from putting some of these bizarre answers here, but they were along the lines of you would ask, how many stones should I eat regularly? And then it would come back, well, 1 stone a day is good for your mineral content and so on, right? So truly, truly disturbing. And of course, the fact that they supposedly have to do this manually tells us that perhaps Blake Lemoine's fear was misplaced, right? Maybe there's something to be afraid of, but not the thing that he was worried about. And then to go a little bit further, this here appeared on the 8th of May, a very nice interview or fact piece with some snippets of interview regarding the European elections that will happen next Sunday. And I really do hope that everybody here who's eligible to vote will go and vote. This is a really important one. And I really, really hope that none of you, absolutely none of you, trusts anything that ChatGPT or any other chatbot tells you about this election or any political process. Because as these guys, these investigative journalists found out, and here actually is a nice English translation, it is absolutely not trustworthy at all, right? What you get out of there is essentially a lot of very nicely polished garbage. And actually dangerous garbage because candidates were invented, the platforms of parties were misrepresented, the roles of principals in the parties were misrepresented, right? For instance, it was said here that Olaf Scholz was the top European election candidate of the Social Democratic Party in Germany, which of course is completely false, right? But it sounds plausible to people who have a need to be politically educated. And if they then go and have that need addressed with current chatbot technology, really, really terrible things happen. So in order to sort of, get a little bit more nuance into this picture, what should we really think of this, right? Are we close to sentient AI that can answer all questions, take all of our jobs, or is it basically a train wreck and a big investment bubble that's about to burst? I think we need to take a step back and ask ourselves a different question, which is, where did all of this come from, and why do we have it, and what does it mean, right? And so for this, I want to briefly take you back into the age of machines, actually the dawn of the age of machines, to this gentleman here, Charles Babbage, a very talented engineer and inventor who lived in the late 1800s, actually in the mid 1800s. So He invented what would have been the first truly universal computer had it been built. And it wasn't built because this funding agency at some point cut his funding. So that's a little sad. But this thing, the analytical engine, he said, as soon as it exists, it will necessarily guide the future of the course of science, right? So he said, this will define science as we know it. And what is this idea that he had in mind? Well, it's actually what we call computation today. And what is computation? The nature of computation, as Babbage, the engineer and inventor, conceived it, and as it has stood until, I would say, about 20 years ago, is clear and precise instructions, clear and precise, that are executed flawlessly. And I want to point out three things to you. People are supremely bad at flawless execution. They're supremely bad at formulating clear instructions, and they're supremely bad with precision. And this is precisely why Babbage thought this would be so useful, because people couldn't do it. This was a time when computers existed, but computers weren't machines. They were people. They were people that were better than average with flawlessly executing clear and precise, usually mathematical instructions. So this is, in some sense, in a nutshell, what an algorithm is. A very precise recipe for data processing, right? And it's really important to realize that what makes this powerful and attractive is that it gives predictable results and behavior. Predictable. And also, it often comes with performance guarantees, which people also don't usually deliver so nicely, right? Performance guarantees, mathematical guarantees. And as a result of this gives us trusted and effective solutions to complex problems. And that's exactly what Babbage had in mind in the 1800s. So since then, there has been tremendous progress in hardware. You've all seen variations of this picture here. We have years down here from actually 1900 to 2015. And of course, after that, it just continues going. And here we have calculations per second per $1,000. And what you can see is that there is this nice line here. And because this is powers of 10, this is really an exponential increase, right? And this is what's known as Moore's law. What this really means is that a computation in 1942, when the first universal computer was finally built, by the way, by Zuse here in Germany, what would have taken 1 year in terms of computation on that machine, the so-called Z3, in 2020 would have taken only 57 microseconds. So that is the awesome improvement in the engineering solutions to the problem of computation, right? What many of you may not know is that there has been even more substantial progress in software. And that has been quantified in an area of operations research known as mathematical optimization, or to be precise, mixed integer programming. Just so I get a sense, who has ever here heard something of mixed integer programming? Just so I get This is very good. I'm very pleased that many of you know this, because this is super important. There is hardly any large industrial company that doesn't use this in one way or another. So it's super widely used and super useful. So here, what has been measured is a 1.5-fold speed up per year, and this compares to 1.4-fold for hardware according to Moore's law, right? Now, you are all scientists and engineers, so you know that when you look at an exponential function and the base goes from 1.4 to 1.9, this is a very big deal, right? And just to illustrate that, this study ran from 1991 to 2007, right? So the study on mathematical optimization, mixed integer programming software. And they basically looked at just the performance improvements due to software without any hardware improvements. And what turns out is that running on 1991 hardware, what took 1 year in 1991, with new algorithms in 2007 on the old hardware only took then 18.22 minutes, solely due to algorithmic improvements in software speed up, right? Now you combine this with hardware speed up, you're going to go down to 5.02 seconds, right? And that means an over 6 million fold speed up in 16 years. There is no other area in human activity, in human history, that has ever produced progress at that scale. None. That is the only area in which a 6 million fold improvement has been achieved over 16 years. So this is why nowadays, of course, algorithms control the world. This article too is actually even before deep learning was a thing, from 2011. The BBC titled that then. And they said basically the maths that computers use to decide stuff is infiltrating every aspect of our lives: financial markets, social interaction, cultural preferences, artistic production, the whole 9 yards, right? All of this when nobody talked about generative AI or deep learning, right? All just thanks to the tremendous improvements that I've talked about briefly already. And the bottleneck in all of this, as you may well know, is human programming capabilities. Because as I said at the beginning, people are not good at formulating clear and precise instructions, and even worse, at executing them flawlessly. So this really sets the stage for the machine learning revolution, which happened shortly after this BBC article appeared. Actually, it was in full swing then, but it hadn't hit the public yet. And for the purpose of this talk, and maybe even beyond, what I'd like you to think about is as of machine learning, not just in terms of constructing models from data, because it is much more than this. What machine learning really is the automatic construction of software that works well on given data. Notice how this goes far beyond supervised learning and unsupervised learning and reinforcement learning and all the nice things that you know about. This is a much broader picture into which all of these other flavors, of course, fit quite seamlessly. As you all know, this is based on statistics and mathematical optimization, and also to a large extent, and actually an increasing extent, on principled experimentation, meaning heuristic mechanisms, meaning things about which some people prove theorems, but the theorems tell you absolutely nothing about what works in practice and when it works and why it works, right? It's still good to prove theorems, by the way. I'm all in favor of this. This is a key ingredient to artificial intelligence, of course, as we all know. But AI is much more than ML, and I'll get back to that later. There's reasoning, planning, multi-agent systems, all these things that you really need in order to have AI have a meaningful impact in the world. So now we live in an age of AI, right? AI technology is posed to transform industry and society. It's seen widely as a key driver of future innovation, growth, and competitiveness. And this is why industry and also governments invest billions and actually trillions of euros, US dollars, whatever you want, into this area. I personally also very, very much believe that AI is one of the keys to solving grand problems of our time, such as climate change and equity and so on, where, of course, if you do it wrong, it actually exacerbates these problems rather than solving them. So we have to be careful how we use it. But why is that the case? Why is AI so tremendously powerful? And this has very much to do with the history of science and engineering. I'd like to distinguish 4 stages in this journey. The first was the stage of experience and experimentation. This is essentially what gave us Gothic cathedrals like the one in Cologne, right? And don't think that back then there were engineers that could calculate whether the structure would stand or fall. They couldn't. That was very much based on experience and experimentation, and only the most experienced masters could actually plan something that would stand rather than fall, right? Even the Sagrada Familia in its original design by Gaudi was based on this principle, right? No science involved basically whatsoever, but tremendous, right? Nevertheless, really impressive. Stage 2 then was to try and understand this intellectually a little bit more thoroughly, and this really then, of course, used mathematics mostly to formalize and gain analytical insight. So now you could have good reasons and explicable reasons for believing that this structure would stand and this structure would fall, right? And that gave us science as we know it today, right? That gave us modern physics, it gave us modern biology, it gave us modern chemistry and so on, and also all modern engineering disciplines. Now, of course, I said modern. I should not have been so quick, because really modern engineering and science disciplines, of course, go beyond mathematics. They use computation very heavily, for instance, to automate or to simulate in particular, right? And that then allows us to do things that with analytical solutions alone, like with closed formulas, for instance, closed form formulas, we couldn't handle. And that allows us to go further and, for instance, design structures that would have been completely impossible based on mathematical principles alone. At least the kind of mathematical principles that give rise to formulae that you can then apply. Stage 4 in this then is AI, and AI is really about handling complexity. It's about learning, reasoning, interaction, and so on. It's just taking stage 3 to yet a different level. And that's why I think that AI is transforming science and engineering, because it's simply the 4th stage of an evolution that has already gotten us incredibly far, right? It has already gotten us from the dawns of civilization to what we have around right now, and it now takes us further. And I want to note that these stages 2 to 4 actually increasingly overcome human limitations and weaknesses, right? Mathematics helps us to think more precisely, something we're naturally quite bad at, right? Unless we're mathematically trained. Stage 3 makes it more efficient, and stage 4 dramatically broadens the scope to which all of this can be applied. So that's why I firmly believe that most of science and engineering will be driven by AI in the near future. And I see that at RWTH and other great universities in the world. I see that happening right now and in the companies as well. So that said, there's 3 more things I want to get across in the 15 minutes I have left. Let's see whether we can manage. The first is I want to talk a little bit about risks in AI and what the real problems are, right? And it's not what Blake Lemoine fears, although I think that fear is one that we should not completely dismiss, but it's not what we should be really worried about right here and right now. It's not strong AI gone bad. It's not human-like AI going rogue on us. That is a possibility, but not the one we should be worried about now. We should be really worried about the incompetent use, and I want to add here the overhyped use, the misinformed use of weak AI, and weak AI is what we currently have. And weak AI is also what Elon Musk will bring you within the 2 to 3 years, where he claims he will produce robots that have the full range of human capabilities. He will not be able to deliver on this. I'm willing to entertain a rather large bet with you or anybody else on this. I will win it handsomely, I believe, which is why I will accept rather unfavorable odds for this one. But what I think we will see is that this will still be weak AI, but weak AI that seduces us to use it in really problematic ways. So this is the big risk. And the nature of this risk is very much tied to something that I refer to as the talent bottleneck. And this can be very easily explained. AI systems are useful and lucrative, right? So you can make money with this. And you cannot just make money by selling or overselling something, but you can really actually make money now applying this stuff in industry. But they are challenging to build, deploy, maintain, and understand. This is not easy stuff, right? Which is why it takes quite a bit of training to do this competently and responsibly. So as a result of this, the AI demand by far is larger than AI expertise supply, right? And this is why AI experts can basically command astronomical salaries, the ones that are really good, right? It's just a market mechanism. So this is good for the few people who really have the expertise. It's not good for the demand side. Why? Because also humans tend to overestimate the capabilities of AI systems, sometimes also their own capabilities, and the failure and limitations when these two things interact. You know, people misestimating their own AI expertise and overestimating the capabilities of the systems that they are responsible for in some sense, right? That leads to failures and limitations that can be quite difficult to detect early. And that then means that underqualified so-called AI experts build, deploy, monitor, and maintain AI systems. And make no mistake, this is happening right now at companies around you everywhere. And it's inevitable because, you know, companies want to deploy AI and there aren't enough AI experts. So what are they going to do, right? They're going to take what's on the market. That leads then to low quality AI systems, and that leads to problems. And these problems will cause quite a bit of damage, economical damage, also other kinds of damage before they're being noticed and hopefully fixed. And that's what you see right now with Google. Now, Google has access to some of the best AI talent in the world. And nevertheless, they rolled out a product, and this is a product. Search is Google's primary product that is deeply, deeply flawed, right? This Verge article isn't good press for Google. It's horrible press, right? And they're not doing this because they are totally incompetent. It's because even they don't have enough real AI expertise to do better than this, right? And they're drinking their own Kool-Aid, meaning they fall prey to their own hype, but that's a different story. So how can we address the talent bottleneck in AI? Well, education is the obvious way, right, at all levels, but especially at the university, especially at universities with engineering prowess and engineering traditions, such as RWTH or TU Eindhoven or KU Leuven or other great technical universities in the world. But also we need to broaden the talent pool. We need to increase the participation by women and also participation across all of Europe. In Eastern and Southern Europe, there is a ton of tremendous potential that is not being utilized the way it could for the benefit of those people and society as a whole. So a lot could be done there. Also, a lot could be done there leveraging the multidisciplinary and broad appeal of AI. And that's great about this conference, because here people come together that don't just do sort of, one technical flavor of AI, but people come together from different disciplines, actually. And that's a very appealing and also a very good idea. And then, of course, you could use AI itself to build and deploy and monitor AI systems. And by that, I don't mean ChatGPT, God no. I mean, that would be a terrible idea currently. But I mean systems that are specifically designed in order to help to build, deploy, monitor other AI systems. And that's actually what my chair here at RWTH and my Alexander von Humboldt professorship is researching. So that part went well, because we're already at part 3 and still have 10 minutes left. Awesome. So, number 3. Here's an article that really warmed my heart. I found it just yesterday, but it's a few days old. I think it was from the 31st of May, so something like last Thursday. And so what this article says, scientists find that artificial intelligence make better beer, right? So better beer is something that many of us appreciate, right? We are very lucky here in Aachen, because just across the border, and here I don't mean our Dutch friends, although they're great as well, but here I mean our Belgian friends in particular, they make some awesome beer, right? We can't, there's no two ways about that. It might not be beer according to the German definition, meaning to the Reinheitsgebot, but it's wonderful beer nonetheless. So notice here, this is from an American website, but indeed what they refer to is a study properly published in Nature Communications, so something pretty high ranking, where the VIB-KU Leuven Center for Microbiology and the Leuven Institute for Beer Research in Belgium use machine learning to make better beer. So the Belgians make better beer than they already can using AI. Is that awesome or what? Now, what is a little bit interesting is to remark, they used machine learning, of course. They didn't use deep learning, and they didn't use Gen AI at all. They used good old gradient boosting, and that should give you to think, right? It should give you to think that the solution to making great things, including great beer, is not always the latest, greatest flavor that everybody is hyped about, but it's basically solid craft. And I would say a machine learning person who doesn't know about boosting, about gradient boosting in particular, they don't know machine learning at all. And they have no business calling themselves a machine learning expert, right? Because any machine learning education should include approaches other than deep learning, period. So, and of course, this fact, coming back to this earlier article here, shows us what kind of bad things happen if we all jump on the same hype train and then go down full speed that track, right? Even those that lay the track then get into serious trouble, right? So we should know more. And this knowing more should start with realizing that intelligence, and really the only way we can judge intelligence is by using human intelligence as a measuring stick. And yes, there are intelligent animals and so on, but that's a fascinating field of study where still much less is known even than about human intelligence. So talking about this is immensely difficult, and the only real comparison we have is human intelligence. Has many ingredients, and certainly one of them is learning, and it's tremendously important. But the other one is reasoning, right? And actually, until about 20 years ago, reasoning was the kind of mental ability that was seen as the prime achievement of human intelligence. Not learning, but reasoning. So therefore, I think it's fair to say that artificial intelligence, at the very least, should include machine learning and automated reasoning, and maybe even more. Automated reasoning, by the way, is pretty much solely responsible for the fact that nowadays we have computer hardware and software that mostly works. All sophisticated computer hardware has gone through so-called SAT solving or SMT solving algorithms, which are automated reasoning algorithms, in order to ensure their correct function. It's actually quite likely that a human engineer team without these tools could not engineer any of the chips that is currently underlying GPUs, CPUs, edge systems, and so on, right? So in reality, what I would claim, and I think I have the data to back it up, is that this here is up to the state by far the economically most important application of AI. It goes before anything else. That might change, of course, right? But so far this is the case because nothing, for instance, NVIDIA's hardware wouldn't work without this. Simply wouldn't work. So there's also knowledge representation and search and optimization and planning and scheduling and multi-agent systems. Multi-agent system is really important because this is how intelligent systems interact towards common goals or in competition, right? And of course, AI systems are in these situations, but humans are also in this situation. In particular, humans interacting with AI systems are in this situation. And then there's ethical, legal, and social issues and so on. And overall, we have a diversity of methods, approaches, and communities. And that is a great strength of the diverse field of AI. The challenge is that the field is fragmented. There's different sub-communities and venues. We have engineering versus foundational and theoretical traditions, which is great because they really can complement each other. We have learning versus reasoning and people that believe that only one and not the other is important. We have a sub-symbolic versus symbolic debate, which I always find a little bit funny because, you know, how could one possibly believe that symbolic reasoning is not important? And the same, of course, for sub-symbolic. We have modern versus good old-fashioned AI, which I think is a completely false dichotomy. We have a competition for attention and funding, which really doesn't help. And what does help is really to realize that real-world AI applications very often draw on methods from different areas. They're not sort of end-to-end deep-learned systems, right? Actually, these are incredibly rare and often not very successful. If you look at what really works in practice, it's often rather different things. Progress often actually combines methods and insights from different areas, just like everywhere in science. Wherever people build really interesting bridges, interesting stuff happens and progress is being made often. And picking winners is notoriously hard. Everybody who plays the stock market knows this, right? So if you don't believe this, ask yourself, would you be willing to invest half of your assets into NVIDIA today? I think nobody has a good answer to this, right? By the way, I pulled everything out last week, so here's my answer. I might put it back in after the NVIDIA stock has come down a little. So there is value in diversity. There is value in bridging between areas and cultures and viewpoints. That isn't just the case societally, but particularly in AI and in science. And in particular, diversity in regulatory regimes, legal systems, in industry, national priorities, and cultural aspects can also be valuable. There's challenges and opportunities, but there's also tremendous value. And this is why it's great that we live in Europe here, where we are at least aiming to be united in diversity, right? And whenever this works, I think it makes us all stronger. And when it doesn't work, it makes us realize how bloody hard that actually is. But that's a good thing to be working on. And it's likewise good to work on diversity in AI and computer science. There are further advantages of diversity, which are complementarity, robustness, and so on. You know, AI built for use and accepted throughout Europe is likely to be valuable far beyond, and therefore European initiatives such as CLARE and ALICE and the Aachen-Leuven-Eindhoven cooperation are tremendously useful. I want to spend my last few minutes on giving you a tiny insight into some of my own technical work because it sort of illustrates this. And this is on neural network verification. It's based on the observation that neural networks tend to be quite sensitive to input perturbations, even if they've been explicitly hardened. And that's a lack of robustness and gives a vulnerability to adversarial attacks. Obviously, here we have a French horn, beautiful instrument. Obviously, here we have a hot dog. Well, no, not a hot dog, but according to some state-of-the-art computer vision model, this is a hot dog. It only has a few pixels modified from here to here and gives this really drastic misclassification. Much more problematic when it happens here, obviously, right? And so therefore, what you need to do is you need to use formal reasoning techniques for robustness verification if you want to be really sure. And there's an entire little field that combines learning and reasoning to do this. I happen to be part of that. And so the key idea is that you want to ensure that all inputs x close to some given input x0. Let's say this is the French horn, and this is everything you can get from the French horn by flipping a few pixels, are classified with the same correct label, namely French horn and not hot dog, right? And so mathematically it means this. Whenever this distance here, in this case L infinity norm, is smaller than the threshold epsilon, the label that should be assigned by whatever you have, in this case a neural network, should be the same. Quite simple, right? So there are tremendous challenges, diverse network architectures, layer operations, activation functions. You have MIP-based, SMT-based, and all sorts of other algorithms and approaches. There's computational complexity. Actually, this is much harder than learning the network verifying, unsurprisingly. And so you could ask yourself, what is actually the state of the art in this? And that's what my team and I have been doing together with collaborators from Leiden University. So we verified methods. We evaluated them on a large number of benchmarks where previously in the literature that has been done on very small sets. There has been a competition that has been going on that seeks to determine a winner. We took another careful look at this. We selected a new benchmark. I don't want to go into technical details here, and then did an in-depth evaluation. And here's what we found. So this is basically a ranking, instances solved. So this is network successfully verified. You can see there's a clear winner. It's this one here, right? Gold. This one gets silver. And now you might just go, let's go with this one, right? This is the best algorithm we have. Not so, because if you look at the verification time, so the performance of the gold medal winner versus the silver medal winner, you see an astounding lack of correlation, right? On some of them, one is an order of magnitude better, sometimes even two than the other. So what you really want to do is use them both. And that happens not just for one network, but for various networks. And it happens for various thresholds epsilon, and it happens for CPU and GPU-based methods. Always this lack of correlation. So what is the state of the art in neural network robustness verification? There is no single best verifier, no single best algorithm that wins. Diversity rules, right? There is performance complementarity. And that holds for all these different methods and settings. And now if you realize that not all verifiers work on all networks type, there's really major potential for parallel portfolios, algorithm selection, and so on, right? So this won a Best Paper Award in 2023 and shortly after appeared in JMLR, which is likely the most prestigious venue in all of machine learning. What about verifier parameters? Well, they influence performance. You should tweak them. Tweaking them is hard. We can use that. We can do that automatically. And this actually works. And in fact, this gave rise to another interesting publication that we have. And ultimately, what you do is you have a neural network. You have inputs. This gives rise to verification problems. So you then have a parallel portfolio of different, in this case, MIP solving techniques, right? You run these in parallel, and that gives you your answer infeasible or robust or optimal, that is not robust. And essentially what that means then is that you can get tremendous improvements. So this is the default running times for verification. This is the portfolio running times. In many cases, you get 2-3 orders of magnitude. You can solve many instances that previously could not be solved at all, right? So this is basically an order of magnitude speed up on average. So time to wrap up. AI will shape the future of science and engineering. Why? Because AI is the new computation. How? By expanding intellectual human capabilities, right? Not by doing the things we already can do well a tiny bit better, but by doing precisely the things that we can do well much better. That's Charles Babbage's idea. And the most prominent and economically impactful example of this right now has nothing to do with deep learning, has nothing to do even with learning, although that might change. Right now, it's the use of automated reasoning techniques for hard and software verification, and increasingly for robustness verification of machine learning methods. So what kind of AI do we need? We need human-centered AI that augments rather than attempts to replace human intelligence. The idea of replacing human intelligence outright is misguided and economically deeply problematic. We need trustworthy AI. We need AI that is lawful, ethical, and robust. And ultimately, that is what will make the difference in the world. So my take-home message, there is an AI revolution going on. It might not be quite what you think, but it is indeed a transition from explicit to automated programming. Large language models might have potential here, but they're currently terrible at this, absolutely terrible. And the reason is that they cannot reason. The reason is that they cannot reason. There is a transition in our engineering culture and scientific culture from mathematics to computation to AI, and that is the basis for science and engineering. The biggest risk as we go up that ladder is not strong AI gone wrong, but human weaknesses, biases, and limitations, in particular our tendency to overestimate ourselves and the products that we make and the techniques that we develop. A little bit more humility would go a long way, and humility used to be a really important thing in science. Nowadays, I have the impression in computer science this has been sometimes forgotten. What we need is trustworthy human-centered AI, and that requires a diversity in AI expertise and perspective. It also requires very serious training. One key idea that can help is to use AI itself to build, deploy, monitor next-generation AI systems, auto AI. Trust me, ChatGPT is not the way to doing that. It is maybe part of a way, but even that remains to be seen. This is our planet. This is the Arctic Ocean. We have a massive problem up there. I'm sure you're all aware of it. I don't give any talk without emphasizing this. We should really try whatever we can in order to address this problem, because this is the real problem of our time. And in order to do that and many other things, we need to aim high, we need to aim true, we need human-centered, trustworthy AI, we need safe, dependable, and sustainable AI. And unfortunately, the kind of things that people nowadays are very hyped up about is neither human-centered, nor trustworthy, nor safe, nor dependable, nor sustainable. So we have a lot of work to do. Let's do it all together. Thank you very much.
Thank you, Holger. I know you all probably have questions, so do I. Unfortunately, we do not have time for any questions. Holger will stay a tiny bit longer, so if you have any questions, you can just catch him after that talk. Thank you, Holger.
Indeed, our technical problems killed that a little bit. Thank you once again. I'll be around.